In 1972, scientists added the very first leap second to human clocks. The reason was simple. Earth was spinning too slowly. The planet was falling behind atomic time, so they added a second to catch up. They did this 27 times over the following decades, always adding, never removing. Then in 2020, something changed. Earth started spinning faster. The records started falling. The shortest day ever recorded since atomic timekeeping began happened on June 29, 2022, when Earth completed one full rotation, 1.5 milliseconds ahead of schedule. And for the first time in history, scientists began seriously discussing removing a second from our clocks instead of adding one, a negative leap second, something that has never been done. That conversation alone tells you something important. The planet beneath your feet is accelerating, and the forces driving that acceleration reach from the liquid iron churning 2,000 miles underground all the way to the glaciers melting at the poles, to the groundwater being pumped out of aquifers beneath your country's farmland, all of them connected, all of them pushing on the same spinning planet. And most people have no idea any of this is happening. The atomic clock noticed before any human consciously registered the change. Not a scientist staring at a screen. A machine ticking in a basement laboratory in Boulder, Colorado, counting time so precisely it would not lose a single second in 300 million years. And one day in 2020, it flagged something. The planet had finished a full rotation too early. Not by hours, not even by minutes, by milliseconds. But to a machine that precise, a millisecond is not a rounding error. It is a warning siren. Something had shifted. The engineers who maintained these clocks did not panic publicly. They quietly filed a report. They updated their models. They started watching more carefully. And what they saw over the following months and years was a planet that was not going back to its old rhythm. It was moving in one direction, faster. And the instruments built to track it were registering something the models had not predicted and could not fully explain with existing data. Understanding why this matters requires understanding what atomic timekeeping actually is and why it was invented. Before atomic clocks, all timekeeping was ultimately based on astronomical observation. The second was defined as a fraction of the solar day, the time it takes Earth to complete one rotation relative to the Sun. Clocks were set to match the sky. By the mid-20th century, scientists realized the sky was not perfectly consistent. Earth's rotation was variable, fluctuating in ways that made it an unreliable foundation for precision timekeeping. Atomic clocks, which count the vibrations of cesium atoms at a rate that depends on fundamental physics rather than planetary motion, offered stability that the rotating Earth could not provide. The second was redefined in 1967 based on atomic transitions rather than planetary motion. For the first time in human history, the fundamental unit of time was anchored to the laws of physics rather than the spinning of a planet. The problem is that human civilization still lives on a planet that rotates. The day begins when the sun rises. The year turns when the seasons shift. All of biology, all of agriculture, all of the intuitive human experience of time is anchored to the planet's rotation, not to cesium atoms in a basement. So the compromise was the leap second. Atomic time would be the foundation for precision. But when atomic time drifted more than 9/10 of a second away from astronomical time, a second would be added or subtracted to keep them aligned. For 50 years, this worked. Earth always needed seconds added because it was always spinning slightly slower than the atomic standard. Then suddenly it was not. Earth is not a perfectly steady spinning top. It never was. The rotation speed changes constantly, responding to forces from every layer of the planet and from objects beyond it. It wobbles. It slows during some periods and speeds up during others. Scientists have tracked this variability for decades using increasingly precise instruments. But what started happening around 2020 was qualitatively different from ordinary variation. The planet began spinning faster than it had in at least 50 years of recorded atomic timekeeping. Not just faster than some baseline, faster than any previously recorded day in the entire history of atomic clocks, and then it kept going. The records kept falling until June 29, 2022, when Earth completed a full rotation 1.59 milliseconds, faster than the standard 24 hours, 1.59 milliseconds. You cannot feel that. Your nervous system does not have sensors capable of detecting a change in planetary rotation speed at that scale. The most sensitive human perception of time operates at scales of tens of milliseconds at best. The rotational acceleration happening right now is orders of magnitude below the threshold of any possible human sensation. And yet it is reshaping the infrastructure of modern civilization in ways that are growing more consequential every year, touching systems that billions of people depend on every single day, without knowing those systems depend on knowing exactly how fast the planet is spinning at any given moment. The systems that depend on knowing exactly how fast Earth is rotating are more numerous and more critical than most people realize. Every GPS satellite in orbit is doing continuous calculations that include Earth's rotation rate as a fundamental input. Every network time server that keeps computers, phones, and financial systems synchronized is ultimately traceable to atomic standards that must be reconciled with Earth's actual rotation. Every satellite in low Earth orbit has its position predicted using models that include the rotation rate. Scientific instruments from radio telescopes to gravitational wave detectors depend on knowing Earth's orientation in space with high precision. Power grids synchronize their alternating current frequency across continental networks using timing references that connect back to rotation measurements. All of these systems are downstream of a single number that is changing faster and more erratically than at any point since the monitoring began. Think about what a millisecond and a half means at the scale of satellite orbits. A satellite in low Earth orbit travels at roughly 7 kilometers per second. In 1 millisecond, it moves 7 meters. If your model of Earth's rotation is wrong by 1 millisecond, your prediction of where the satellite is has an error of 7 meters built into it before you even start. For a communication satellite, that might be acceptable. For a precision imaging satellite mapping infrastructure or monitoring ice sheets, it is not. For the timing signals that financial markets use to sequence transactions, it is not. For the landing guidance systems of commercial aircraft operating in low visibility, it is not. The millisecond matters enormously, and it is not staying still. This is why timekeepers around the world held a quiet but serious set of meetings after the 2020 acceleration began. And it is why they started discussing the negative leap second, the deletion of a second from the world's clocks to keep up with the faster rotating planet. In 50 years of leap second management, the direction of correction had always been the same. Add a second to slow the clocks down. Now, for the first time, the planet was moving in the opposite direction. And the question of how to respond was genuinely new. Engineers who had spent careers managing the consequences of positive leap seconds had never had to think seriously about the reverse. Their software had never been tested for it. Systems that were not coded to handle the jump from 23 hours, 59 minutes, 59 seconds to 23 hours 59 minutes. 60 seconds had caused problems with positive leap seconds in 2012, 2015 and 2016. Cloudflare, one of the largest internet infrastructure companies in the world, experienced a major outage during the 2017 leap second. Reddit, Mozilla and LinkedIn all reported issues during past events. A negative leap second, a backward jump in time, was expected to be far more disruptive because nothing in the history of computing had ever been designed or tested against it. And then there is the deeper question that the negative leap second conversation raised. If the planet is accelerating, what is accelerating it? And is this acceleration going to continue or reverse or do something else entirely? Answering those questions requires following forces that most people never think about. Forces that originate in places no human has ever visited and never will. Forces that began operating before life existed on this planet, and forces that trace in part to things as ordinary as the water being pumped from the ground beneath farmland in California, India, the Arabian Peninsula, and dozens of other regions around the world. Every one of them is connected to every other. Every one of them is pulling on the same spinning planet simultaneously. And following each one leads somewhere stranger than the last. We begin underground because that is where the oldest and most powerful forces originate. Miles beneath your feet, there is a liquid ocean of iron and nickel slowly churning in total darkness at temperatures that would vaporize any material humans have ever built. The outer core of Earth begins about 1,800 miles beneath the surface. That depth exceeds the width of the continental United States from the Atlantic coast to the Pacific coast. Down there, pressure is so extreme that iron, which is solid at the temperatures present on the surface, exists as liquid. It moves in massive currents driven by heat rising from the solid inner core below and by the rotational forces of the planet above. Those currents generate Earth's magnetic field, the invisible shield extending tens of thousands of miles into space that deflects the solar wind and protects the atmosphere from being slowly stripped away over geological time. Every compass that has ever pointed north, every bird that has navigated by a magnetic field, every ancient mariner who found their way across open ocean using nothing but a needle and a container of water was depending on the liquid iron churning 2,000 miles underground. But the outer core does not just generate the magnetic field. It also influences how fast the planet spins at the surface, thousands of miles above. The outer core and the solid mantle sitting above it are not perfectly locked together mechanically. They can slide relative to each other. Exchanging angular momentum in a process scientists call core-mantle coupling. The mechanism works because the magnetic field generated by the core's currents threads through the mantle above, creating a magnetic linkage between two layers that cannot touch directly. When patterns in the core's circulation change, they change the magnetic linkage, and that changes how angular momentum is transferred between the core and the mantle. When the core slows its rotation relative to the mantle and the surface above it speed up in compensation. The physics is the same as two wheels connected by a belt. Change the speed of one and the other responds. Scientists studying seismic data from earthquakes that travel all the way through the planet have documented correlations between changes in core flow patterns and changes in Earth's rotation speed over periods of decades. The seismic waves that travel through the core carry information about the material they pass through, encoded in the speed and shape of the waves as they emerge on the far side of the planet. By comparing seismic records across decades, researchers can track changes in the core's behavior. The correlation between those changes and rotation changes is confirmed and documented across multiple independent research programs using data from seismic networks on every continent. This is an established observed relationship in planetary science, not a hypothesis awaiting confirmation. What remains harder to quantify is the current situation. Why are core flow patterns changing right now in ways that appear to be accelerating the surface rotation? Some researchers believe the patterns are cyclical, operating on timescales of roughly 60 to 70 years, alternating between phases that push the rotation faster and phases that slow it back down. If this cyclical interpretation is correct, the current acceleration may be part of a natural pattern that has been repeating since before humans developed any precise timekeeping. Historical rotation data extracted from ancient eclipse records and tidal measurements going back centuries shows evidence of multi-decade fluctuations consistent with a roughly 60-year cycle. But fitting a cycle to historical data is not the same as predicting future behavior. The core is a complex fluid system governed by magnetohydrodynamics in a geometry and at pressures that cannot be replicated in any laboratory. Predicting its future behavior with confidence is beyond current capability. Other researchers think the current shift has characteristics that distinguish it from previous cycles, suggesting something new may be happening. The magnetic field, which reflects the structure of the core's fluid motions, has been changing in ways that appear unusual in the context of recent centuries. The rate of drift of the magnetic North Pole accelerated significantly since the 1990s, moving at speeds that required updating the World Magnetic Model, the international standard used by navigation systems, ahead of its normal 5-year revision schedule. The South Atlantic anomaly, a region where the magnetic field is unusually weak and where satellites experience increased radiation damage, has been expanding and deepening. Whether these magnetic changes are connected to the rotational changes through a shared cause in the core's dynamics, or whether they are coincidental manifestations of independent processes, remains an open question. What is not in dispute is the inaccessibility of the thing being studied. The deepest borehole ever drilled by humans reached about 7.5 miles into the crust, the Kola Superdeep borehole in Russia, which took over 20 years to drill and encountered temperatures so high at that depth that further drilling became mechanically impossible. 7.5 miles, the outer core begins 1,800 miles down. No instrument has ever touched it. No drill ever built has come remotely close. The only way scientists can examine what is happening at those depths is through earthquake vibrations that travel through the planet and emerge on the other side, carrying information in their wave shapes about the properties of the material they pass through. Every piece of knowledge about the core was extracted from indirect evidence, interpreted through theoretical models. And those vibrations are currently telling scientists that something in the core has changed its behavior. A force 2,000 miles underground, unreachable and invisible, is nudging the clock of every living day on the surface of this planet at an even deeper level, buried inside the outer core itself. There is the inner core, a solid ball of iron roughly the size of the moon, sitting at the very center of the planet under pressures so extreme that iron solidifies despite temperatures rivaling the surface of the sun. For decades, the inner core was assumed to be essentially static, a locked anchor at the planet's center, while the liquid outer core moved around it. Then evidence emerged in the 1990s that it might be rotating slightly faster than the rest of the planet, detected through subtle changes in how seismic waves traveled through it over time. Waveforms from earthquakes in the South Sandwich Islands, recorded at a station in Alaska, showed tiny but consistent changes across decades, suggesting the inner core's crystalline structure was presenting a different face to the seismic waves as years passed. If the inner core were rotating at the same speed as the rest of the planet, this would not happen. Then in 2023, a study published in the journal Nature Geoscience presented evidence that this picture had changed again. Researchers analyzed decades of seismic data from earthquakes at multiple locations and found that the inner core appeared to have decelerated, slowing from its previously faster rotation to something matching the outer layers. Some interpretations went further, suggesting the inner core may have actually begun rotating very slightly in the opposite direction relative to the surface, a phenomenon with no confirmed precedent in the observational record. This specific interpretation remains scientifically contested. Multiple research groups have analyzed similar datasets and reached different conclusions. But the foundational observation that seismic waves passing through the inner core are arriving differently today than they did in the 1990s and 2000s has been confirmed by multiple independent teams. Something changed at the center of the planet. The exact nature of that change is being debated. The fact of the change is established. The rotational consequence flows through the coupling mechanisms connecting every layer. The inner core and the outer liquid core surrounding it exchange angular momentum through magnetic forces and viscous interactions at their boundary. If the inner core shifts its rotational behavior, it affects the liquid outer core. The outer core affects the mantle through core-mantle coupling. The mantle affects the crust and surface. A change at the center works its way outward over timescales of years to decades. What the center is doing now is already showing up in the rotation data at the surface. The center of your planet is actively participating in determining the length of your day right now without your knowledge and without your consent. The inner core raises a more general point about human knowledge of the planet. We have mapped the surface of the moon in greater detail than we have mapped the inside of our own world. We have more precise data about the topology of Mars than about what lies at the center of Earth. The deepest borehole ever drilled barely scratched the surface. The center is 4,000 miles away in the direction of straight down, unreachable by any technology that exists or is currently being designed. Scientists can study it only through the vibrations it transmits when earthquakes shake the planet, through the magnetic field it projects through the mantle, and through the gravitational signal it contributes to the planet's overall gravity field. Every piece of information about the inner core was extracted from indirect evidence. And yet, from that indirect evidence, scientists have learned enough to detect when something there has changed. The center of your planet is not just a scientific curiosity. It is actively participating in the length of your day. Between the iron core and the ground you stand on lies the mantle. A layer of rock more than 1,800 miles thick, 3 times the distance across the continental United States, constituting the bulk of Earth's interior by volume. The mantle is solid but not brittle. Under the enormous temperatures and pressures present at those depths, over timescales of millions of years, solid rock deforms and flows. The viscosity of the mantle is approximately 10 to the 21st times the viscosity of water, a number so large it is almost meaningless as a direct comparison. Imagine a material so thick that it would take millions of years for an object to settle a few inches through it, and you begin to approach the time scale on which the mantle moves. Yet it does move driven by heat from the core below and cooling from the surface above in slow convection cells that span thousands of miles. This mantle convection drives the tectonic plates that make up Earth's surface. North America is drifting away from Europe at about an inch per year, carried on a plate whose motion is ultimately driven by mantle convection. The Himalayas are still growing because the Indian plate is still being pushed into Asia. The Pacific Ocean is dotted with island chains formed by hotspots, places where mantle plumes rise through the mantle and melt through the oceanic crust above, leaving a trail of volcanoes as the plate moves over them. Hawaii sits above one of these hotspots today. The chain of older Hawaiian islands stretching northwest marks the path the Pacific plate has taken over the hotspot over millions of years, a geological record of both the plate's motion and the hotspot's existence, preserved in volcanic rock. The connection to rotation is through mass redistribution. As convection moves material from one location to another over geological time, the distribution of mass within the planet changes. When mass distribution changes in a spinning body, the rotation changes correspondingly. Mantle convection is far too slow to explain the rotation changes measured over years or decades. But over geological time, it has been one of the dominant forces shaping how fast Earth spins, and the mantle interacts with the core through the boundary between them, influencing the flow patterns in the outer core that drive both the magnetic field and the core-mantle coupling that affects the surface rotation. Within the mantle, seismic imaging has revealed two enormous anomalies sitting near its base on opposite sides of the planet. One lies beneath Africa, the other beneath the Pacific Ocean. Each is roughly the size of a continent, spanning thousands of kilometers. They are denser than the surrounding mantle, hotter and compositionally distinct. Seismic waves slow down when passing through them, which is what gave rise to their technical name, large, low shear velocity provinces. They have been sitting there for hundreds of millions of years, surviving the breakup of the supercontinent Pangaea, the mass extinction at the end of the Permian that eliminated 96% of marine species. The dinosaur-ending impact 66 million years ago, and every other geological catastrophe of the past several hundred million years. Some researchers believe these structures organize the patterns of mantle convection, acting as anchors that determine where hot material rises toward the surface and where cooler material descends. The positions of major mantle plumes correlate with the edges of these structures in ways that suggest a causal relationship. Others believe they interact with the flow of the outer liquid core above them, influencing where and how the magnetic field generating currents are organized. Some scientists have proposed that they represent ancient oceanic crust that subducted into the deep mantle billions of years ago and has been sitting there ever since, too dense to continue sinking and too isolated from active convection to be carried away. Their exact nature and origin remain debated. Whether they are contributing to the current rotational acceleration is genuinely unknown, but they are real, enormous, and sitting at the exact boundary where core-mantle coupling occurs. The story of ice and rotation is the most visible part of this account, and the one most directly connected to decisions being made by governments, industries, and individuals right now. When ice accumulates on land over thousands of years, its weight presses the bedrock down. When it melts, the bedrock rises. This process has been unfolding for 11,000 years in response to ice that melted at the end of the last glacial maximum, and it is still happening today at measurable rates. The last glacial maximum peaked roughly 20,000 years ago. Enormous ice sheets covered most of North America, most of Scandinavia and parts of northern Asia. The Laurentide ice sheet over North America was in places 2 miles thick. It extended from the Arctic to what is now the Ohio River in the American Midwest. Its total volume was roughly 26 million cubic kilometers of ice. Its weight depressed the bedrock of the North American continent by hundreds of feet. Hudson Bay sits today where some of the deepest ice was, and its bedrock still lies far below sea level, depressed by ice that has been gone for thousands of years and still rising back toward equilibrium. When the ice melted, the weight was removed and the land began rising. This process, called glacial isostatic adjustment or post-glacial rebound, is still measurably active 11,000 years after the ice disappeared. In Scandinavia, the crust is rising at about an inch per year, measured by GPS, by tide gauges, and by the positions of ancient shoreline, features now sitting high above the current sea level. Ancient harbours that were at sea level when the Vikings used them are now sitting meters above the water, lifted by rebounding bedrock. The harbour of the ancient city of Ephesus on the Turkish coast, a major port in the ancient world visited by St. Paul and home to one of the 7 wonders of the ancient world, is now miles from the coast because the land has risen and the silted up river pushed the coastline seaward. Parts of northern Canada show rates of rebound comparable to Scandinavia. Hudson Bay is gradually becoming shallower as the bedrock beneath it continues its slow upward journey. The rotational consequence of this rebound is real and measurable. As land rises in formerly glaciated regions, mass moves upward and toward higher latitudes, slightly closer to the rotation axis. Mass moving closer to the rotation axis in a spinning system speeds it up. Post-glacial rebound from the last ice age is a confirmed contributor to long-term rotational change, and it will continue for thousands of years, regardless of what happens to ice sheets today. The mantle has its own schedule determined by its viscosity, and it does not respond to human timelines. The rebound that will occur over the next 10,000 years is already committed by the ice loss that happened 11,000 years ago. The current ice loss is writing its own version of this story for future millennia. Greenland is losing hundreds of billions of tons of ice per year, confirmed by satellite gravity measurements from the GRACE mission that have tracked this loss in detail since 2002, mapping where on Greenland the ice is thinning fastest and how the total mass is changing year by year. Antarctica is losing ice from multiple regions, with losses concentrated in West Antarctica, where the marine ice sheet instability is most active. GPS sensors placed directly on Antarctic bedrock are already detecting the first measurable signs of modern rebound in regions where ice loss has been most rapid. The land is beginning to respond to ice loss happening right now. Future generations will inherit a planet still adjusting to what is occurring today, still rising in places where our ice sheets are currently retreating, still redistributing mass in response to changes set in motion by this generation. The immediate rotational effect of current ice loss comes from the mass redistribution itself. When ice sitting at high latitudes near the rotation axis melts and flows into the ocean as water, it redistributes toward lower latitudes and particularly toward the equatorial ocean, which is farthest from the rotation axis. Mass moving from near the axis to far from the axis is like the figure skater extending their arms outward. It increases the moment of inertia and should slow the rotation. This is a confirmed physical effect. Scientists have calculated it precisely using satellite gravity data and models of ocean circulation. The mass of Greenland's annual ice loss, redistributed into the global ocean, has a computable decelerating rotational consequence, and yet Earth has been speeding up. The resolution to this paradox is that multiple forces are acting simultaneously, pulling the rotation in different directions. And right now, the forces driving acceleration are stronger than the forces driving deceleration. The core mantle coupling is currently pushing toward faster rotation. Certain components of the atmospheric circulation have been net accelerating. The post-glacial rebound from ancient ice has a component that contributes to acceleration by moving mass toward the poles and the rotation axis. These effects are currently outweighing the decelerating effect of current ice loss, but the ice redistribution effect grows steadily as more ice melts. At some point, the balance will shift. Whether that happens in years or decades depends on trajectories that current models cannot precisely predict. The atmosphere adds a contribution that is both well documented and changing in ways that are difficult to model fully. The atmosphere's total mass presses down on every square inch of Earth's surface with a force that adds up to roughly 11 quadrillion pounds across the entire planet. This mass moves in organized circulation systems that span hemispheres. The jet streams are narrow bands of fast-moving air at high altitudes that can reach speeds over 200 miles per hour. The trade winds blow steadily across the tropics in both hemispheres, so reliable that European explorers exploited them to cross the Atlantic and Pacific. The polar vortex organizes cold air over the Arctic and Antarctic in winter, and when it breaks down, it sends frigid air surging into middle latitudes in events that have become more frequent and more extreme as the Arctic warms. Each of these circulation systems involves enormous masses of air moving at significant speeds. Moving mass carries momentum. When that momentum is transferred to or from the solid Earth below through friction between the atmosphere and the surface, the rotation responds. This is called atmospheric angular momentum transfer, and it is a confirmed, documented, quantified phenomenon. During El Niño events, when sea surface temperatures in the tropical Pacific warm and reorganize global atmospheric circulation, the length of a day changes by fractions of a millisecond in ways that can be tracked in real time and explained quantitatively by the atmospheric changes. The models that account for atmospheric contributions to rotation variability are detailed and well validated against decades of observations. What is less clear is how the changing atmosphere of the coming decades will affect this contribution. The jet streams are shifting under Arctic amplification, the phenomenon where the Arctic warms roughly 4 times faster than the global average. The South Atlantic anomaly has been expanding and deepening. As the temperature difference between the Arctic and the tropics decreases, the temperature gradient that drives the jet streams weakens. The jet streams become more meandering, more variable, more prone to large north-south excursions that bring extreme weather events to mid-latitudes. A more variable jet stream means a more variable atmospheric angular momentum. A more variable atmospheric angular momentum means a more variable and less predictable rotation. There is also the seasonal breathing of the atmosphere. Every year as the Northern Hemisphere summer arrives, the atmosphere warms and expands slightly. Its mass is roughly constant across seasons, but its distribution changes. Warm air expands outward, moving mass fractionally away from the rotation axis. The planet's moment of inertia increases slightly. The rotation slows slightly. In winter, the atmosphere contracts. Mass moves inward. The rotation speeds up slightly. This cycle repeats with extraordinary regularity every year. The length of a day in January is measurably different from the length of a day in July. By an amount your body cannot feel, but that atomic clocks register clearly. The planet breathes with the seasons, and its breathing changes how fast it spins. The moon has been slowing Earth's rotation for 4.5 billion years through tidal friction, and the cumulative effect of that braking is the most dramatic transformation the rotation has ever undergone. Every time you watch ocean water move, tides creeping up a beach and retreating, you are watching a mechanism that has been steadily transferring Earth's rotational energy to the lunar orbit for longer than complex life has existed. The mechanism works through tidal bulges. The moon's gravity raises bulges in Earth's oceans on the side facing the moon and on the opposite side due to the interaction between gravity and orbital dynamics. Earth rotates faster than the moon orbits. The tidal bulges get dragged slightly ahead of perfect alignment with the moon by the planet's faster rotation. The moon then pulls backward on these misaligned bulges, exerting a gentle but continuous braking force on Earth's rotation. Energy removed from the rotation is transferred to the moon, which responds by slowly spiraling outward to a higher orbit. The moon is retreating from Earth at 1.5 inches per year, confirmed by laser ranging measurements using reflectors placed on the lunar surface by Apollo astronauts. The cumulative effect over billions of years has been enormous. When the moon first formed from the debris of the giant impact, roughly 4.5 billion years ago, it was much closer to Earth, perhaps only 10 to 20,000 miles away compared to its current 250,000 miles. Earth was spinning much faster. A day on the young Earth lasted only about 6 hours. 4.5 billion years of tidal braking have slowed the rotation to the current 24-hour period, while the moon has moved outward to its current distance. Every second that the moon has retreated farther corresponds to Earth's rotation slowing by a corresponding amount. The geological record confirms this history. Ancient tidal rhythmites. Layers of sediment deposited by tidal cycles in shallow ancient seas can be counted like tree rings. Each lamination represents one tidal cycle. By identifying seasonal patterns within those laminations and counting tidal cycles per season, scientists calculate how many days were in a year when those sediments formed. Data from tidal rhythmites 620 million years old indicates a year of about 420 days, each lasting about 21 hours. Ancient coral fossils from 400 million years ago show about 400 days per year with days of roughly 22 hours. These are physical counts of preserved biological and sedimentary records. They are cross-checked against each other and against the physics of tidal evolution, and they are internally consistent across multiple independent measurements from different locations and geological periods. On the timescale of millions of years, the days will continue to get longer as tidal braking continues. But on the timescale of decades and centuries relevant to the current rotational acceleration, tidal braking is one of the smaller forces in play. The atmosphere, the core, the ice, and human water management are currently producing rotational changes that exceed the tidal braking signal over short periods. The moon will win eventually. On the timescale of billions of years, it always does. But right now, other forces are temporarily overwhelming the lunar braking. Polar wander connects the rotation, the ice, the core, and human activity in a way that reveals how deeply every part of this story is interconnected. Earth's rotation axis is not fixed relative to Earth's surface. The poles move. The geographic North Pole today is not in exactly the same location it occupied 100 years ago or 1,000 years ago. This drift, called polar wander, is driven by changes in how mass is distributed within and on the planet. As the distribution of ice changes, as post-glacial rebound moves mass upward in formerly glaciated regions, as groundwater is redistributed by human extraction, the planet's mass distribution changes. When mass distribution changes in a spinning object, the rotation axis shifts. The pole drifted westward throughout most of the 20th century. Then, around 1995, its direction changed. It began drifting eastward, and the rate of drift increased. NASA data confirmed in 2021 that Earth's rotation axis had shifted toward the east at an accelerating rate since the late 1990s. The suspected primary causes are ice loss from Greenland and groundwater depletion. The very act of melting ice and pumping groundwater is physically moving the North Pole across the surface of the planet. The Chandler wobble adds another dimension. Discovered in 1891 by American astronomer Seth Carlo Chandler, it describes a small irregular oscillation of Earth's rotation axis relative to Earth's surface, causing the geographic North Pole to trace a rough circle about 30 feet wide over a period of roughly 14 months. 30 feet on the surface of an 8,000-mile wide planet. And yet this wobble has been tracked continuously for over a century and shows up clearly in data from around the world. Scientists can track a 30-foot circle traced by the rotation axis of a planet by analyzing the arrival times of radio signals from objects billions of light years away, using very long baseline interferometry where radio telescopes on opposite sides of the planet simultaneously observe the same distant quasar and measure tiny differences in signal arrival time. The Chandler wobble's 14-month period is not arbitrary. It is determined by Earth's internal structure. The distribution of mass inside the planet sets the rhythm of the wobble. If you knew the exact distribution of mass throughout the entire planet, you could calculate the Chandler period from first principles. The fact that the observed period is 14 months is one of the pieces of evidence that constrains models of Earth's interior. And here is the implication that researchers find significant. If the internal distribution of mass changes significantly through mantle movements, core shifts, or surface mass redistribution from ice loss and human activity, the wobble's period will change. So far, the 14-month cycle holds, but the direction and amplitude of the wobble continue to evolve in ways being actively monitored and studied. Around the year 2000, the Chandler wobble slowed significantly and nearly stopped for a period of several years. Various explanations were proposed and debated. Most researchers concluded that a combination of atmospheric pressure, changes in ocean bottom pressure were responsible for the near cessation. The wobble resumed. But its subsequent behavior has continued to evolve in ways that track the changes in mass distribution happening across the planet from ice loss and groundwater depletion. The wobble, the polar drift direction, and the rotation speed change are all expressions of the same underlying reality. The mass distribution of the planet is changing, driven by processes operating from the core to the ice sheets to the aquifers beneath human farmland. Human activity has added itself to these planetary forces in ways that were not recognized until researchers noticed that the rotation data did not match what natural processes could explain. When scientists account for ice loss, post-glacial rebound, atmospheric changes, and core mantle coupling, and then compare the result to the actual measured rotation, there is a residual, a gap between what the models predict and what the instruments measure. Investigating that gap led to the discovery of the human contribution. The primary human contribution comes from groundwater extraction. Over the 20th century, the expansion of industrial agriculture and the growth of cities in arid regions drove massive extraction of water from underground aquifers that accumulated over thousands of years. The Ogallala Aquifer beneath the American Great Plains contains water that accumulated during the last ice age. The aquifers beneath the Arabian Peninsula contain water from periods when the region received far more rainfall than today. The aquifers beneath northern India and Pakistan are being depleted at rates that satellite measurements have confirmed are not sustainable. And over the past century, humans have been extracting this stored water at rates that enormously exceed the natural recharge. In some cases, mining water that accumulated over tens of thousands of years at a rate that will deplete it within decades. When groundwater is extracted, it eventually enters the hydrological cycle. Used for irrigation, it evaporates from fields and transpires through crops. It flows into rivers and eventually reaches the ocean. Mass that was stored underground in continental interiors. At latitudes where it sat relatively close to the rotation axis, moves to the global ocean, where it redistributes toward equatorial regions farther from the axis. The moment of inertia of the planet changes. The rotation changes. A study published in 2023 by Kiwion Seo and colleagues quantified this effect for the period between 1993 and 2010. Researchers found that groundwater extraction during this period shifted Earth's rotational axis by about 31 inches to the east and contributed a measurable signal to the rotation speed. Among the factors examined, groundwater depletion had the second largest effect on polar drift after Greenland ice loss. The groundwater effect was smaller than ice loss overall, but not negligible. It was large enough to be separated from other signals in the data and attributed specifically to human water management. This finding represented something historically unprecedented. For the first time in 4.5 billion years of Earth's history, a biological species had measurably altered the rotation of the world it lives on through the routine activity of managing its water supply, not through any intentional planetary engineering project, not through any awareness that this was happening while it was being done, through irrigation and groundwater pumping conducted over decades for entirely ordinary agricultural and industrial purposes, with no intent to affect the planet's rotation and no knowledge that such an effect was occurring. The planet's rotation carries a human fingerprint now, and that fingerprint is growing larger as human water use scales upward. Large reservoirs work in the opposite direction. When water is impounded behind a dam, mass that would have flowed to the ocean is retained on land at higher latitudes. The Three Gorges Dam in China holds back an estimated 40 cubic kilometers of water in its reservoir, water that would otherwise have flowed down the Yangtze River to the Pacific Ocean. The reservoir is located at roughly 30 degrees north latitude. That is considerably closer to the pole than the equatorial Pacific Ocean, where the water would end up without the dam. By holding the water at that latitude, the dam is keeping mass fractionally closer to the rotation axis than it would be otherwise, slightly counteracting the decelerating effect of groundwater that has already reached the ocean. The Hoover Dam on the Colorado River, the Aswan Dam on the Nile, the Kariba Dam on the Zambezi, and thousands of other major dams collectively hold back enormous quantities of water. The net balance of all human water management on Earth's rotation involves these competing effects, and their relative magnitudes depend on the geography of where water is being taken from and where it is being stored. Beyond water, human changes to the land surface have potential rotational consequences that are less precisely quantified but real in principle. Deforestation changes how water is stored in soil and vegetation and how it moves through the hydrological cycle. A forested hillside stores water differently from a cleared hillside, holding it in the soil and releasing it gradually rather than letting it run off quickly into rivers. Urbanization replaces permeable soil with impermeable concrete and asphalt, routing rainfall into storm drains and rivers rather than into groundwater. Agricultural expansion moves water from natural storage in wetlands and forests into croplands, where it is transpired more rapidly into the atmosphere. Each of these land use changes moves mass in ways that affect the rotation. The individual contributions are small enough that quantifying them requires models that integrate human land use data with hydrological and atmospheric models at global scales, a research frontier being actively developed. The practical consequences of rotational changes come into sharpest focus when you examine the infrastructure that depends on knowing exactly how fast the planet is spinning. Global navigation satellite systems are the most familiar example. Every GPS satellite does continuous calculations that include Earth's rotation rate as a fundamental input. The navigation satellites broadcast timing signals. Your receiver compares those signals to calculate distances to each satellite, and from those distances calculates a position. The calculation assumes certain things about where the satellites are and how the ground is moving beneath them. If the rotation input is wrong, the position output is wrong. For casual navigation, a few feet of error is acceptable. For aviation approach and landing systems that guide aircraft to runways in near-zero visibility, the tolerances are measured in feet and errors matter directly. For precision agricultural equipment that plants seeds in passes overlapping by only a few inches across thousands of acres, centimetre-level accuracy is required, and errors have direct economic consequences. For autonomous vehicle guidance that must distinguish between adjacent lanes on a highway, errors matter for safety. For geodetic survey work that monitors infrastructure and measures ground deformation, sub-centimetre accuracy is required. For all of these applications, the quality of Earth rotation data fed into the position calculation is a binding constraint on the accuracy achievable. The financial markets represent an application of precise timing that most people have never connected to Earth's rotation. Modern markets execute transactions at speeds measured in microseconds. To prevent market manipulation, transactions across exchanges and clearinghouses are time-stamped with microsecond precision. These timestamps are synchronized using timing infrastructure that ultimately traces back to atomic standards maintained in alignment with Earth's rotation. When a leap second is added, every financial system in the world has to handle the extra second correctly. The 2012 leap second caused documented problems at multiple financial institutions, including incorrect timestamps and system crashes. The 2015 and 2016 leap seconds caused issues at major internet infrastructure providers. A negative leap second, a backward jump in time, would pose a far more severe version of the same problem for systems that have never been designed or tested against backward time jumps. The prospect of a negative leap second was one of the primary motivations behind the decision made in November 2022 at the General Conference on Weights and Measures to abolish leap seconds entirely by 2035. Instead of correcting clocks every few years to keep atomic time within 1 second of astronomical time, atomic time and astronomical time will be allowed to drift apart. Corrections will only happen when the accumulated drift exceeds a minute, which is not expected to occur until well into the 22nd century. This decision has been made. It is official. And what it means is that for the first time in human history, the official time standard of civilization will formally decouple from the rotation of the planet that civilization lives on. Human time and planetary time will be different things, allowed to diverge in ways they have never been allowed to diverge before. This decoupling is a rational engineering response to the growing difficulty of keeping the two aligned in an era when the rotation is changing faster and less predictably than at any previous point in the history of timekeeping. It is also a recognition that Earth's rotation is no longer a stable foundation for global civilization in the way it appeared to be when atomic clocks were first invented. The planet is changing. Its rotation is changing. The systems that depend on precise timekeeping must adapt to a rotation that is becoming less predictable, not more. Antarctica deserves detailed examination because what is happening there is more complex and more consequential than most public reporting captures. Antarctica is a continent buried under ice that in some places reaches nearly 3 miles thick. Underneath that ice is terrain that most humans have never seen. Researchers are studying this hidden landscape with airborne radar that can see through miles of ice from planes flying grid patterns across the continent. What that radar has revealed has repeatedly surprised the researchers who expected to find simple geology beneath the ice. What the radar found beneath parts of the West Antarctic ice sheet changed risk assessments for the region fundamentally. Over 400 subglacial lakes sit under the ice, liquid water formed by geothermal heat from the bedrock below, sitting in complete darkness under crushing pressure. Some of these lakes are connected by subglacial rivers, channels of flowing water that exist under miles of ice. These lakes act as lubricant between the ice and the bedrock. When they fill and drain, the ice sheet above slides more or less easily across the rock. This affects how quickly ice moves from the interior toward the coast, where it eventually breaks off as icebergs. The subglacial lakes are part of the machinery driving how fast Antarctica loses mass to the ocean. The West Antarctic ice sheet has been losing approximately 150 billion tons of ice per year on average during the past decade, confirmed by satellite gravity measurements. That rate is accelerating. The bedrock beneath the ice sheet sits in a bowl shape, with higher ground around the edges and lower ground in the center. As ice retreats from the edges, ocean water can potentially flow in beneath the remaining ice, contacting the base where it is warmest. Each step of retreat makes the next step easier. The West Antarctic ice sheet contains enough water to raise global sea levels by about 3.5 meters if it collapses completely. This would not happen in years. It would likely unfold over centuries. But the rotational consequence of redistributing 3.5 meters of equivalent sea level rise from near the South Pole to the equatorial ocean would be significant and lasting. East Antarctica was supposed to be separate from this concern. Then in 2022, satellite data confirmed that the Conger ice shelf, a floating platform of ice attached to the East Antarctic coast and roughly the size of Rome, collapsed entirely in a matter of days. An ice structure that had persisted for thousands of years disintegrated in less than a week. It was the largest ice shelf collapse ever recorded in East Antarctica, and it happened during a period when East Antarctic temperatures hit unprecedented levels, reaching more than 70 degrees Fahrenheit above normal at some locations. Ice shelves matter because they restrain the glaciers flowing behind them. When the Conger Shelf collapsed, the glaciers it had been holding back lost their restraint. The radar mapping of terrain beneath East Antarctica revealed that the bedrock has networks of valleys, basins, and channels carved deep into the rock, some extending well below sea level and connected through submerged pathways to the Southern Ocean. Warm ocean water reaching these channels could contact the base of East Antarctic glaciers and melt them from underneath. Invisibly, without any surface sign until significant loss had already occurred. East Antarctica contains enough ice to raise global sea levels by 50 to 60 meters if fully melted. This is not expected to happen soon, but the geographic vulnerability is confirmed. The fortress has gaps in its walls that were not visible until radar looked through the ice to find them. The fortress is more exposed to the warming ocean than was believed before these surveys were conducted. The thermohaline circulation, the global conveyor belt of ocean water that carries heat from the tropics toward the poles and returns cold water from the depths, is one of the most important climate systems on Earth. Without it, northern Europe would be dramatically colder, the Amazon would receive less rainfall. Ocean ecosystems from the surface to the deep would be fundamentally different. And Earth's rotation helps drive it through the Coriolis effect. As Earth spins, it deflects moving water and air to the right in the northern hemisphere and to the left in the southern. This Coriolis deflection emerges purely from the fact that the ground beneath the moving fluid is itself rotating, moving faster at the equator and slower toward the poles. The great ocean gyres, the enormous circular current systems that dominate each ocean basin, rotate the directions they do because of it. The trade winds exist because of it. The monsoon systems that bring seasonal rainfall to billions of people are organized by it. The entire large-scale circulation of the ocean and atmosphere runs on the organizing principle provided by Earth's spin. When Earth's rotation speed changes, the Coriolis effect changes with it. Confirmed measurements show the Atlantic thermohaline circulation has slowed significantly over the past century and is now at its weakest point in over 1,000 years. The primary cause is fresh water from melting ice diluting the dense salty North Atlantic water that drives the sinking circulation, combined with warming temperatures, reducing the temperature, contrasts, fueling the flow. Some researchers consider a significant further weakening or outright collapse of this circulation a genuine possibility within the current century under high emissions scenarios. If the circulation collapses, the redistribution of ocean heat around the planet would change dramatically. Ocean mass would redistribute. Ice formation and melt patterns at the poles would change. All of those changes would feed back into Earth's rotation through the mass redistribution mechanisms that run throughout this entire story. The ocean floor is not passive either. At mid-ocean ridges, magma rises from the mantle, cools and forms new crust, pushing the existing seafloor outward in both directions. The mid-Atlantic ridge is pushing the Atlantic Ocean wider at roughly the rate fingernails grow. At subduction zones where plates collide, old dense oceanic crust dives back under the continents and sinks into the mantle. This process has been operating continuously for billions of years and continuously redistributes mass beneath the ocean. Individual earthquakes leave immediate marks on the rotation data. The 2011 Tohoku earthquake off the coast of Japan, magnitude 9, shortened Earth's day by about 1.8 microseconds and shifted the planet's figure axis by about 6.5 inches. The 2004 Sumatra earthquake, magnitude 9.1, shortened Earth's day by about 6.8 microseconds. The 1960 Chilean earthquake, the most powerful ever recorded at magnitude 9.5, had even larger rotational effects. These are confirmed measurements from seismic and geodetic networks. A single geological event lasting minutes changed how fast the planet spins and where its axis points. Scaled at across thousands of earthquakes per year, the continuous creep of tectonic plates and the slow sinking of massive slabs of old ocean floor and the seafloor and the tectonic system become active participants in the rotation story. At every timescale, from minutes to millions of years. The precision instruments that track all of these changes have transformed what scientists can know about Earth's rotation compared to any previous era. The Very Long Baseline Interferometry Network uses radio telescopes on opposite sides of the planet that simultaneously receive signals from quasars billions of light years away and measure tiny differences in signal arrival time. From those differences, the orientation and rotation speed of the planet can be calculated to extraordinary precision, detecting changes in the length of a day down to a few tenths of a microsecond. The network spans multiple continents, including stations in the United States, Europe, Asia, Australia, and Antarctica, providing truly global coverage and redundancy. The Earth orientation parameters it produces are published regularly, sometimes daily, and distributed to navigation satellite operators, timing authorities, and scientific institutions around the world. The GRACE satellite mission uses 2 spacecraft flying in precise formation to measure tiny variations in Earth's gravitational field by tracking how the distance between the 2 spacecraft changes as they fly over regions of varying mass. Where mass concentrates below, the leading spacecraft accelerates slightly. By mapping these changes over time, scientists have produced continuous global maps of mass redistribution on and within the planet. The data confirms ice loss in Greenland and Antarctica in detail that no ground-based measurement program could match. It confirms groundwater depletion in aquifers across every continent. It confirms seasonal water storage in river basins and mountain snowpack. It confirms the slow rise of land through glacial rebound, all from orbit. And every kilogram of mass that moves anywhere on or within the planet changes the gravitational field that GRACE measures, which means GRACE is effectively watching the rotation change in real time by watching the mass move. In the rotation data collected over the past 2 decades, there are signals that the models do not fully explain. Fluctuations that do not cleanly correspond to any known forcing, patterns that repeat but whose source has not been pinned down. These residuals are real and have been noted by multiple research groups working independently. One candidate for some of the unexplained fluctuations is the deep ocean. The abyssal circulation has been poorly measured compared to surface and mid-depth currents, because reaching the deep ocean with instruments is expensive and technically difficult. Recent deep ocean monitoring campaigns have found that these bottom waters are warming faster than expected, and that their circulation patterns are shifting in response to changes in the rate of Antarctic bottom water formation. If the rate or properties of this formation are changing, the distribution of mass in the deep ocean is changing. If that change is not captured in current rotation models, it could account for part of the unexplained residuals. Another candidate involves how the atmosphere responds to warming at the poles. As the Arctic warms faster than the global average, the temperature difference between the equator and poles shrinks. This difference is the driving force behind the atmospheric circulation. A smaller temperature gradient means weaker driving, which means a more variable and less organized jet stream. The models that capture atmospheric angular momentum transfer were calibrated against decades of data from a climate that is no longer the climate we have. Whether they remain accurate under a more variable atmospheric circulation is an active research question that does not yet have a definitive answer. The Milankovitch cycles provide the longest perspective on Earth's rotational history and connect the current situation to a much larger context of astronomical forcing. Across tens of thousands to hundreds of thousands of years, Gravitational interactions between planets in the solar system slowly change the shape of Earth's orbit and the angle of its axial tilt. Earth's orbital eccentricity varies on cycles of roughly 100,000 years. The tilt of Earth's rotation axis, currently about 23.5 degrees, varies between roughly 22 and 25 degrees on a cycle of roughly 41,000 years. The direction in which the rotation axis points wobbles through a complete circle over 26,000 years, a motion called axial precession. These cycles are named after Serbian mathematician Milutin Milankovic, who spent years calculating their combined effect on the amount of solar energy reaching different latitudes at different seasons. His calculations, refined by decades of subsequent work and validated against the geological record of ice ages, show that the alignment of these orbital cycles determines when ice ages begin and end, when the combination of orbital parameters reduces summer sunlight reaching the northern hemisphere, where most of Earth's land mass is concentrated. Ice builds up. Ice ages develop over thousands of years. When the orbital combination reverses and summer sunlight increases, ice ages end in deglaciations that raise sea levels, redistribute mass, and change the rotation. We are currently in an interglacial period. Based on orbital parameters alone, the next glacial period would eventually begin in roughly 50,000 years. The human contribution to atmospheric greenhouse gas concentrations may extend this interglacial significantly because the additional warming from elevated CO2 counteracts the orbital cooling that would otherwise trigger the next ice age. Some modelling studies suggest human emissions have already committed the planet to an interglacial lasting tens of thousands of years longer than it would last without human influence. The rotational consequences of this modification of the Milankovic cycle are one of the genuinely open questions in long-term planetary science. The tipping points that climate scientists discuss represent locations in the climate system where forcing that may appear gradual can suddenly produce rapid and largely irreversible change. The West Antarctic ice sheet instability is the most directly relevant. The Greenland self-reinforcing melt feedback is another. The weakening of the Atlantic thermohaline circulation is a third. The Amazon dieback, where progressive deforestation and warming shift the rainforest toward a drier state that generates less of its own rainfall, is a fourth. Each represents a system that, past a threshold, changes its behavior faster than current trends would suggest, and in ways difficult or impossible to reverse on human timescales. What makes tipping points particularly difficult to navigate scientifically is that they are often invisible until very close. The system looks stable, data looks normal. Then a threshold is crossed and the change comes faster than models predicted. This has happened repeatedly in Earth's past. The end of the last ice age was interrupted by periods where temperatures jumped by several degrees within decades, not millennia. The Younger Dryas, a sudden cold reversal that lasted about 1,200 years and ended abruptly, demonstrated that climate systems can flip states quickly when conditions align. The rotation record from those transitions, preserved in ancient sediments and coral, shows corresponding rapid changes in spin rate. The honest scientific summary of the current situation is this: Earth is confirmed to be spinning faster than it has in at least 50 years of atomic timekeeping. The main categories of forces responsible are confirmed: core mantle interaction, redistribution of ice from the poles, atmospheric angular momentum transfer, long-term post-glacial rebound, and a measurable contribution of human water management. These forces interact with each other. The system has feedbacks. The current acceleration will not continue indefinitely. Less certain is exactly how each of these forces is evolving and how they will interact over the coming decades. The models are good and getting better. The measurements are precise and becoming more comprehensive. The gaps between what models predict and what instruments measure are real and being actively investigated. Some residuals likely reflect forces or interactions not yet fully characterized. The near-term trajectory over the next few decades will be dominated by the interplay of the core-mantle coupling cycle, the ongoing redistribution of ice and atmospheric variability. The longer-term trajectory over centuries to millennia points toward gradual slowing as tidal breaking and ice redistribution dominate. Days will get fractionally longer, not in ways anyone alive today will notice, but in ways the geological record will preserve. What almost all models agree on, regardless of scenario, is that the variability in Earth's rotation will increase. The swings between faster and slower periods will become larger and less predictable as the forcing mechanisms become more energetic. A warming atmosphere holds more energy and redistributes it less regularly. More energetic weather means stronger and less regular atmospheric angular momentum signals. More ice loss means more rapid mass redistribution events. The rotation will not just change in one direction. It will oscillate more wildly around its long-term trend. The geological past provides the most important context. Earth has been spinning for 4.5 billion years. It has survived impacts that melted portions of the crust, mass extinctions that eliminated the majority of species, episodes of severe glaciation in which ice reached the equator, and periods of extreme warmth in which there was no polar ice at all. Through all of it, the rotation continued. It changed, but it never stopped. That resilience is real, but the rate of change matters. The changes that Earth has survived were spread across timescales of millions to billions of years in most cases. The forces now acting on the rotation are producing changes on timescales of years to decades. A civilization cannot adapt on million-year timescales. It must adapt on the timescales of decades, which are the timescales on which the current changes are unfolding. The precision instruments now monitoring the rotation are better than they have ever been. The very long baseline interferometry network is more comprehensive. The satellite gravity missions provide continuous global mass distribution data. Seismic networks are more sensitive and more numerous. The models assimilating all of this data are more sophisticated. Every year the picture becomes more complete. Every year the residuals between models and measurements narrow slightly as new sources of forcing are identified and characterized. What you now understand that most people walking through their day do not know is this: the day is not a fixed thing. The rotation is not a constant. The 24 hours you live inside today is not the same length as the day someone experienced 1,000 years ago. It is longer than the day a dinosaur lived through when days were 22 hours and a year had 400 of them. It will be longer still in 1,000 years when tidal breaking has extracted a little more rotational energy and transferred it to the slowly retreating moon. Every layer of this planet is in motion, in conversation with every other layer, exchanging momentum and energy in a continuous negotiation that has been running since before life existed. The core speaks to the mantle speaks to the crust speaks to the ocean speaks to the atmosphere speaks to the ice, and the ice speaks back all the way down through the ocean and the crust to the mantle and eventually to the core. A planet-wide system of feedbacks running continuously for 4.5 billion years without pause. Human activity has joined that conversation in the past century, adding its own signals through groundwater extraction, reservoir construction, land use change, and the greenhouse gas emissions that are reorganizing the atmospheric circulation and accelerating the ice loss. The signals are measurable, the fingerprint is real, and it is growing larger every year. The atomic clock in Boulder, Colorado is still ticking. It is counting every millisecond with a precision that would not lose a second in 300 million years. It is recording the length of every day as the planet completes each rotation. The engineers and scientists who read its output are watching something that no previous generation of humans could see clearly enough to understand. A planet in dynamic disequilibrium, a rotation that is responding to forces operating simultaneously at every scale, from subatomic quantum transitions in cesium atoms to the gravitational pull of the moon across 250,000 miles of space. The world is accelerating. The instruments are watching. The story is still being written in real time, in milliseconds, on a spinning planet that has never been entirely still and has never been entirely understood. And somewhere in the gap between what the models predict and what the instruments measure, there is something waiting to be discovered, something about the planet that nobody has yet identified, something that, when found, will make the story more complete and will almost certainly reveal that the planet is more complicated, more interconnected, and more responsive to the forces acting on it than anyone currently believes. The clock keeps ticking, the planet keeps spinning, and the conversation between every layer of Earth continues without pause, recording everything in the length of the day, waiting for instruments sensitive enough to read what it says on a spinning world that is moving just a little faster than it was yesterday, for reasons that reach from the iron core to the ice sheets, to the water beneath the fields where your food was grown, all of them connected, all of them real, all of them part of the same unbroken conversation that the planet has been having with itself since before the first living thing drew the first breath on the surface of this turning world.